Hi, my name is Abigail Mueller, and welcome to today's presentation, Geometry's Lookalikes, Understanding Similar Triangles. Mint chocolate chip ice cream and cookies and cream ice cream are similar, but they are not the same. That's a definition you might hear in everyday life. But in the world of mathematics and geometry, two shapes are similar if they are the same shape, but different sizes. Let's understand similar triangles a little bit better. Similar triangles have corresponding angles that are equal. If you match up the angles in the same positions in both triangles, they'll have the same measure. For example, 115 degrees and 115 degrees. On further inspection, I can see that all corresponding angles are indeed equal. When we further understand similar triangles, we see that their corresponding sides are proportional. This means that the ratio of the length of a side in the first triangle to the length of the corresponding side in the second triangle is constant for all sides. This constant ratio is called the scale factor. The word proportional here means the relationship is consistent. In ratios, we look at the relationship between numbers, often comparing them. Let's look at the scale factor, or this constant ratio between these two similar triangles. There are two different ways to look at it. 4 is reduced to 2 by a difference of 2. That's the ratio. Here you could go the reverse way and see that 2 is enlarged or increased by 2 to get a corresponding length of 4 on the similar triangle. Well, what criteria guarantees that two triangles are similar? Sometimes you can't always just trust your eye. One of the first theorems is the angle, or AAA, to check for similarity. If the angles of one triangle are respectively equal or equivalent, then the two triangles are similar. Check out these angles. They are equal in both of the triangles. Therefore, they are similar. But what happens when your angles aren't quite so easy to figure out? Let's look at the next one. 37 degrees, 33 degrees, 110 degrees, and 110 degrees. Indeed, the angles are the same on all three corners. But here's an interesting hint. Do you really need to check all three angles? Or would 2 be sufficient? Think about it. 60 plus 60 is equal to 120. You know that in order to be a triangle, all three angles must equal 180 degrees, or they will look very different from one another. These are the same. 37 and 33 are equal to 70. So the next one has to be 110 degrees. Another theorem is the side, or SSS. This checks for the proportions. If the corresponding sides of two triangles are in proportion, meaning they have the same scale factor, then the triangles are similar. I'm going to look at the ratios of the corresponding sides to see if these are similar. I'll start first with the longest sides and then work my way down to the shortest. Here we go here. I find a ratio of 7/5. When I check the other sides, 21 divided by 15, I'll divide each side by 3. That's 7/5. It's looking good so far. I'm hoping my third side will be the same. 14 divided by 10, divide the numerator and denominator by 2, and I get 7/5. Indeed, the ratio is the same. The sides are proportional. The triangles are similar. Yet another interesting theory is the side-angle-side theorem. If the ratio of the lengths of two sides of one triangle are equal to the ratio of the lengths of two sides of another triangle, and the included angles are equal, then the two triangles are similar. Let's look at a problem to help prove this theory. Just by looking at it, I'm not quite sure if these triangles are similar. So let's put the theorem to the test. I know that angle B and angle Z are both 90 degrees because these are right triangles. So they have that in common. When I check the sides, I will get a ratio of 2/3 to 2/3. Indeed. Now you'll notice I have a little X over here. That's just my instructor's mistake. I'm going to say this one is not correct, but let's use the theorem to prove it. I'm going to check these triangles that are within one another, triangle EAB and triangle DAC. I know that their angle is similar because they share it. So when I look at the ratio of the sides, I know when I divide 9/12, notice I don't have the length of this one because if something's off with these two, this one doesn't matter. 3/4 is not equivalent to 12/17. The ratio is off. These triangles are not similar. Perhaps if something changed here, like this went down to 4 inches or 4 centimeters, which would leave this at 12/16, which would become 3/4, then I might be closer to getting two triangles that are similar. Here's a problem that my teacher gave me to do. She said that this would help me better understand similar triangles. It helps me to solve and figure out how tall this tree is using similar triangles. Is that something that would happen in real life? You betcha. People are always measuring tall buildings, trees, flagpoles, the distance from windows to the ground using similar triangles. In the fields of architecture and construction, they also use similar triangles in their blueprints to build small models, to design roof slopes, to build A-frame homes, to build ramps, and to make sure that walls are straight with similar right triangles. Did you know in the fields of navigation and maps, satellites use similar triangles to help locate you? This would be very helpful if you were lost in the woods with all those tall trees. Cartographers also use similar triangles to measure distances and to survey things like rivers and the distance across from them. In the fields of photography and optics, very fancy lenses that are able to zoom in and zoom out with precision use similar triangles in their design. Thanks for joining me today in our presentation about similar triangles. Here's a joke to close us out. Why were the similar triangles kicked out of math class? Because they kept copying each other's angles. See you later.